Hello, this is the presentation of our work on generating heavy-tailed synthetic data with normalizing flows. With the ever-growing advancements in machine learning methods and due to their effectiveness in presence of massive amounts of data, developing methods for generating synthetic data has become one of the most essential tasks in the field. Having control and insight into data generation process lets us enrich training sets to make our models more performant, fair, and private. In this work, we look into synthetic data generation for data with long and/or mixed tail behavior using normalizing flows. The advantage of normalizing flows over other types of generative models is that they allow us to control the tail behavior of the estimated density. Normalizing flows transform a simple distribution into a complex one by applying a sequence of invertible transformation functions. The simple distribution is usually set to multivariate normal. However, we know that the Lipschitz continuous transformations will produce target distributions with the same tail index as the base distribution. Therefore, the choice of base distribution becomes important when generating long and mixed tail data, and can lead to the success of the flow model in capturing the tail behavior of the target distribution or its failure. We look into the use of differentiable mixture densities for base distribution of the flow model as a way to mitigate the problem of differences in support and topologies of the base and target distributions. We apply our experiments to a dataset sampled from a modified Niels funnel and the real-world credit fraud dataset. We empirically show that in case of the bivariate Niels funnel, the mixture-based distribution provides the best performance and more stable training for synthesizing long-tail data via flow models. As for the credit for our dataset, we showed that the discriminative model trained to distinguish between fake and real data has the most difficulty doing so when the flow model is trained with a mixture-based distribution. For future work, we want to understand why mixture models perform best in this specific task. We want to experiment with additional datasets, and we want to use tail-specific information to make it easier for the flow model to capture nuanced tail behavior of the target distribution.